Okay, so I've split screen here so that we can do all the work on the left-hand side and then we can actually do it on the graph on the right. So, remembering our algorithm of steps, we're going to find vertical asymptotes, test their limits, horizontal or oblique asymptotes, test their limits, x and y intercepts, and then the new thing is to find the critical points, doing the first derivative tests, and then we'll put it all together and finish the sketch. So, first things first, as always, we'd like to put it in a factored form. So we've got x minus 2, x plus 1, all over x minus 3. So step 1, vertical asymptotes. Of course, it's the values for x. It's going to get me a 0 on the bottom. I know we all can see 3 is the vertical asymptote. And then instead of doing test points like we did before, we'll do our new limits. So this is the left side limit. So it's limit as x approaches 3 from the left of f at x, and the limit as x approaches 3 from the right of f at x. We'll use the factored form. So we now, in our head, choose a number that's to the left of 3, it's like 2.9. So 2.9 minus 2 is going to stay positive. 2.9 plus 1 is positive, and 2.9 minus 3 is negative, which means we're going to get negative infinity. Now we'll choose something just to the right of 3. So let's say 3.1. Again, minus 2 is going to make that positive. Plus 1 is still positive. And on the bottom, it's now positive. And so we have positive infinity. So now we can go over and add this information to our graph. So we know we're going to have a vertical asymptote at 3. And according to our limits tests, we see from the left that it's going to go down to negative infinity. And from the right, it's going to go up to positive infinity. Now you notice I've sort of cheated a bit, and I know what the graph is going to look like, so I've given us a graph that's got a lot more room at the top of the x-axis than at the bottom. And if you look back in your graph, you'll remember that that's necessary for this. Okay, so there's our vertical asymptote. Like I said, steps are the same, just with the new limit notation. Next step in our algorithm is to find horizontal asymptotes. To do that, we investigate n and m. N is the degree in the top, which is 2. M is the degree in the bottom, which is 1. N is greater than m, which means there's no horizontal asymptote. But since they're bigger by 1, there could be an oblique asymptote. So to find oblique asymptotes, we actually do the division. So it is x squared minus x minus 2, all being divided by x minus 3. So I'll give you a second to do that long division. If anyone needs more time, you can pause, of course. Okay, so we'll go through and say, okay, what number multiplies by x to get x squared? So that's x. Do the multiplication, it's x squared minus 3x. We'll subtract, be careful here, it's minus 1 minus minus 3, which is like plus 3, so that's 2x. Now we go repeat. What number do I multiply by x to get 2x? And that's 2. Rainbow, 2x minus 6. Oh, I forgot to bring down my negative 2. Subtract again. Again, this is negative 2 minus minus 6, which is like plus 6. So we have a remainder of 4. So this is nice doing this long division because it's got its 2 bits of information. First, it gave us the oblique asymptote, the equation for the oblique asymptote. So let's actually graph that. we know that that's a straight line, y equals x, plus 2, so it's got a y-intercept of 2. So it's going to go through here. Actually, we'll plot a few points because I like to do that. So it's intercept of 2, and it's up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. Because the slope is 1. Plain old x function, but of course moved up 2. So I'll do those lately, and then I'll get my actual asymptote, and I'll put it right there. Maybe just adjust it a bit. Of course, your ruler is going to be much more accurate than mine. And we have that. Now, as we recall, last unit, we didn't have a way to determine whether this oblique asymptote, if it was coming from above or below, but we did learn 2 days ago that we can use the directrix. And so we have the directrix being the remainder over the denominator, which in this case is x minus 3. So we're going to do our test points on the directrix. So we'll do a limit as x approaches first negative infinity, because we're talking horizontally now on D, and then the limit as x approaches positive infinity on D. So you choose a very, very big negative number, put it into the directrix. Obviously the plus 4 is still going to stay positive, but a negative number, minus 3, is insignificant, and it goes negative, so it means it comes from below. And when you put in positive infinity, you'll put in a really big number. The plus 4 is not affected. And then a billion minus 3, the minus 3 is insignificant, it's still positive. And it'll be plus, which means our graph is going to be above the oblique asymptote. So when we look over at this from the left, the negative infinity, we see that it's going to come from below the asymptote, and to the right, or positive infinity, it's above. And we would have anticipated that from experience, seeing that we already have part of the graph below the asymptote and part of the graph above, but finally we have some math to back that up. Okay, so already you can see that it's the same steps as before, but a little bit more work. All right, step 3 in our algorithm is to find x and y intercepts. So we know the x-intercept is when y equals 0, and the y-intercept is when x equals 0. So we'll have to go back and remind ourselves of this, our equation. So there it is. So y equals 0 is 0 equals x minus 2 bracket x plus 1 all over x minus 3. Again, if you recall, we don't really need to write the bottom because the first step shows that the bottom gets multiplied by 0 and that disappears. That leaves us with just 0 equals x minus 2 and x plus 1. That's going to result in 2 x-intercepts, the first one being at 2 and the second one being at -1. So those 2 x-intercepts we can actually graph on our graph. So there's the x-intercept at 2 and the x-intercept at -1. Next, we're going to have a y-intercept. Again, we'll go back up to the top. This time I'm going to use the original function because I find it easier to sub in 0 there. So y equals, instead of x squared, it's 0 squared minus 0 minus 2 all over 0 minus 3. So that's -2 over -3, which is just 2 over 3. So that means there's this y-intercept at 2 over 3, which when we sketch is roughly there. So really we've got a good shape of our graph, and had this been last semester, we probably would stop right here. We have lots of good information. We can probably see the shape of the curve at the bottom and the shape of the curve happening at the top. But we have this new bit of information in the calculus that allows us to find step 4, find critical points, and be able to find exactly how high it rises and exactly how low the other one goes down. And that's what the next video will do.